So we're on lesson 1B.8, understanding rate of change. So it's going to be 3-part notes, but they're not very long notes, as you can see. Okay. So for part 1, it's about rate of change from linear to nonlinear functions. Okay. The key concept here is that rate of change measures how one quantity changes in relation to another quantity. So when we talked about rate of change, you may see me referred to as ROC, R-O-C, the rate of change. Okay. The rate of change is your change in your dependent variable over the change in your independent variable. Okay. When you have that triangle in mathematics and in physics, that stands for change. Okay. If you're in physics, you may have heard it called delta y over delta x. Okay. And that's where that comes into play. So this is what we're talking about. How is one quantity changing compared to another quantity? And that's going to be our rate of change. So with linear functions, so back when you first started talking about this, a linear function has a constant rate of change called the, what's the constant rate of change called for linear? The slope. Okay. So for example, if we have the distance traveled at a constant speed, right? I'm driving the same speed for X amount of time. Therefore, that's an example of a constant rate of change. If a car travels at 60 miles per hour, what is that telling me? After the first hour, the car is gone how far? 60 miles. After the second hour is gone how far? 120 miles. After the third hour, it's gone 180 miles. So this is an example of a constant rate of change. Does that make sense? So, because I'm adding on the exact same amount every single time. All right. With a constant rate of change, that means you're adding or subtracting the same amount repeatedly, right? Now, what happens if I don't have that? Can we identify rates of change even if it's not, which is what we're leading into for 1.9. But here we go. Identifying rates of change. So in your bell ringer, yeah, you're due now with your you're due now with your Desmos. Oh, there we go. Desmos, you were talking about looking and see where positive rates of change, right? When you have a positive rate of change, that means as you're reading your graph from left to right, your y increases as your x increases. So what I'm looking at for a positive rate of change, as my y increases, my x are increasing, right? That's going to be my positive rate of change. Your negative rate of change is your y values decrease as your x values decrease. So here's my graph. As my x values are getting bigger, my y values are getting smaller. So this is a positive ROC. This is a negative ROC, rate of change. All right. The next one we have is for nonlinear. When you have a nonlinear rate of change, rates change at a different interval. Okay. So when you have nonlinear, your rates are changing at a different interval. For example, let's talk about a real world example. Temperature throughout the day. So temperature throughout the day, what tends to happen when you wake up in the morning? It's cold, but then it does what? It gets hot, right? So it's a gradual increase, or it's a pretty fast increase, right? So let's describe it as a fast, because my Alexa will tell me it's currently 67 degrees, but you can expect a high of 93. Alexa, how am I going from 67 to 93? How are we getting there? Make it make sense. Okay. And then we get around lunchtime, and the afternoon is usually what? It's not much change, right? It's just slow. It's slow change. It's pretty steady, right? So it's a slow / steady change, whichever word you want to describe. It's more of a steady, in my opinion. And then what happens in the evening? It gets cold, but does it get as cold as fast as it did in the morning, as it warmed up in the morning? No, it gets cold slow, right? So around us, nothing is happening in a perfect linear motion, right? things are happening at their own pace, at their own rate of change, because we're not a perfectly linear society. And to think that we are is a little off, a little weird. Okay. So for example, here, we're going to go through and make sure that we can identify from examples if we have a linear model or a nonlinear model. And if we have a nonlinear model, why? What is it? So first one, the growth of a plant over 4 weeks. So I measured my plant on week 1 and it was 2 inches. Then I measured my plant on week 2 and it was 4 inches. Then I measured my plant on week 3 and it was 8 inches. And then I measured my plant on week 4 and it was 16 inches. Is my plant's growth being modeled by a linear situation? And why is it not? It's not constant. A constant means that you're adding or subtracting the same amount every single time to get from one to the next, right? What's taking place here in our pattern? I'm doubling. I'm multiplying by 2 to get one from to the other. Do you guys remember what kind of model this is? It's called what? I heard something. Exponential. No, so not linear, but it is exponential. And that's because it has a constant ratio. So instead of a constant rate of change, I have a constant ratio of change, which means that I'm either multiplying or dividing or doing both. Okay, so let's look at our second example. I want you to take a minute, make your own decision. A phone battery drains at first hours, I was at negative 20%. At the second hour, I was at negative 15%. At the third hour, I was at 10%. Do you think it's linear or non-linear? And tell me why. All right, we got a linear. So this is pretty interesting, right? So the way they decided to record how the phone is draining is that I have less than 20%. I have less than 15%. I have less than 10%, right? So they're recording it based on the percentage. But those percents are equally changing. This is an example of a problem that could be tricky, that could be considered either linear or non-linear, depending on what you're analyzing, right? If I'm analyzing just 1%, like how did my phone change over that hour, right? And I'm changing that 20% every X amount of time, I'm losing 20%, then that would make it exponential, right? Anytime that we have a percentage that we're taking away or adding to, that's going to tell us that we are generally dealing with an exponential model, right? In this case, because of how it's written, it's actually a fair if you wrote linear, because you're saying that each time I'm going from but I'm subtracting, right? Well, actually, if I went from negative 20 to negative 15, it's the reverse of that, right? But it doesn't matter because it's still what? It's linear because it is constant. It's addition, right? I'm adding or subtracting the same amount each time. So this would make it linear, and that's because I have a constant rate of change. For some reason, I feel like I can't write anymore. Like my hand has forgotten how to make letters. Maybe it's the tablet. Okay, so key things I want you to remember. Coming from Algebra 1. Linear is going to always have a what? A linear model is going to always have a constant rate of change. Okay, it's going to be this constant rate of change throughout. All right, nonlinear rates vary as, and this is as your intervals change. They vary at intervals. So your rates may not be the same, right? All right. Um, rates may not be the same. Thank you. I realized that I didn't give us a long enough line for that. Okay. So going back to your Desmos activity, notice how the waves were an example, clear example of nonlinear, right? Because they were like literally going up and going down and going up and going down. When you were watching Karen's run, Karen, her whole function wasn't linear, but she had linear pieces, right? And they were separated into intervals. Okay, that's where that comes from. All right, when you are doing this, you want to look at interval to determine if its rate is constant. Okay, you want to look at each interval. Just each interval, you're going to find the change in y over change in x per interval. So that means if you have multiple intervals, you're going to have to do the change in y over the change in x more than one. Okay. All right, so that concludes our 1B.8 part 1.